Okay, so how is the festival vibes wherever you are? Currently, Durga Puja, Navratri going on. Okay, so okay, if you don't want to tell me, uh, so let's get started. There, Happy Shoshti. Thank you, Happy Shoshti. Mm. So, hmm. So I was always very good turnout in my sessions. 9 to 10 students is good. Uh, so so we are going to get started on generative modeling, especially in case of images. Okay, and we will see that. Okay, so we have gone to some details in variational autoencoder. So we'll go further details in that. Okay, and you can see my slide, na? Now, better now. Now what we have to do is so in the video that I post, means are you able to see the things clearly? Because like only part of the screen I can show, other the screen I means the people's icon come in the place. So is it okay that way? So and the volume is low as well, na? Volume complaint I've got. So I will fix that. I'm going really busy these days actually. So the volume issue will be taken care of. Okay, but the screen part is okay. So you are able to see when you watch the videos. Okay, maybe I'll just start. So so variation autoencoder, of course, we'll learn from the paper only. Uh, I've already downloaded the paper, and so we'll go into further details today actually. Um, so previously also we have done it, but it is a very important paper actually, very important concept in AI. So okay, mm, so the paper is which one? Lot of variational paper as you can see. Which one is the correct one? This is the one. Hmm. So here we have already seen like what is our task. Okay, let me show from the presentation I had made. I had shown previously as well. So here so what is our task actually? Task is written somewhere, not written maybe. So I had written the task. Maybe it is written somewhere. Okay. Okay, huh. Here it is written. So it is again annotated as well. So what we are doing is that you have an image X here, okay, and you are putting it through encoder. So neural networks, okay, can be CNN, can be transformer, anything. And so what it outputs are two values, mu and sigma. Okay, now okay, so what do you actually do? You sample from a 0 1 normal distribution and you put mu and make this reparameterization. Okay, so epsilon is the 0 1 normal distribution, and doing this reparameterization you get a mu sigma square normal distribution. Okay, so you feed this distribution to the decoder and you get the reconstructed image. Okay, and well, the problem formulation starts with that both the whole structure, all the parameters are represented by theta, but after that they find that it is not possible to optimize a single theta. So they break down into two parameters, two uh, group of parameters. One is phi as the encoder, and theta means the phi is the parameters of the encoder and theta is the parameter of the decoder. Okay, up to this any doubt? Up to this any doubt? No doubt, right? So now we will understand what is the importance. Why do we need variation encoder in the first place? Okay, so so these are some of the tasks which can be not able to write here. Okay, open in Keynote. This will help us. Not able to open. Okay, so let's do it like this. This is the one. But this is not annotated. Okay, that's okay. So here what are the tasks we have is detect when an image looks unusual. Okay, so what does that mean? Okay, so unusual, what do you mean by that? So it is written anomaly detection. Okay, so what it means here is that while you are doing this process, what you are able to do is you are able to learn the so this images keep coming in the training. Okay, one image, then second image, third image, like all the images in the data set are put through this structure so that the model is trained. So what does the model learn is the distribution of the data. You understand? Distribution of the data, the px, what we call is a px. So what we learn from here, still not able to write. So what we learn from here is px. Px is the distribution of the data. Okay. So anything which does not fit in the distribution, suppose, so this is the normal distribution, say just any distribution, and suppose any point is here. Okay, it does not fit in the distribution. What does that mean? It is anomaly. Okay, it is not part of the distribution, so we can make anomaly detection with this. Okay, so practically what you have to do, so you take the image. Okay, and then you what you do is we put through the encoder, you get a latent representation z, which we have seen here. Okay, now so if the model works, okay, when you put z through this decoder, the image look should look the same or similar. Okay, something like that, or a better way maybe uh, I think this is the way. Okay, so if it is not part of the distribution, okay, so then it is called out of distribution. Okay, so that is one part of it. Filling missing part of the image. Okay, so you put the image, the missing, suppose one part of the image is cropped out, you put through the decoder and the decoder will generate on that missing part. Okay, so that is remove noise or super resolve images. Okay, so for that what you can do is So um, so for that, these are some of the tasks. Okay, exact detail let's not go. Okay, so this is it. Okay, now the problem scenario is that we have to learn the distribution. You have to learn the parameter theta here, which at first was the parameter of the whole structure of the whole neural network. Okay, but then we do it into phi and theta. Okay, so okay, now latent variable z, if you know latent variable z, if you know the distribution of z, then you can generate x. Okay, so that is a generation problem. Okay, one generation task you can do. You can generate new images given the z. Okay, varying the mu and sigma. Okay, so that is one task. Okay, so you need to learn this distribution px, which can be written as this. Okay, but if z is higher dimension, which it usually is, suppose like 50 dimensional, so you cannot do the integration. Okay, so this integration path to calculate px to estimate ps is intractable. Okay, so you cannot do that. Next thing what you can do is, means like we're understanding it more, not the solution. This is not the solution. Okay, so this is Bayes theorem. Okay, now this is intractable. Okay, you cannot find that, so then you cannot do this as well. Okay, so you cannot make a latent code. That's what they mean. Okay, okay, so these are the thing. Now now the problem formulation, which is in the paper as well. Okay, but we will see some derivation as well. Okay, so let me show some derivation as well. Uh, mm, okay, so what we are about to do is, I forgot. Yes, this is the one. So the problem we had was that we cannot calculate this integration here. Yes, yes. I will send it. Actually I was really busy, so I have not sent these things. Okay, I'm very sorry for that. I'll upload all of the details of the presentations and everything. Um, I think today midnight. Yes, I'm very sorry for that. Just I was too busy actually. Sorry. But today midnight I will upload every detail. Okay, every presentation, everything I've used. Okay, so 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 this is what we have. Okay, this is the paper. Achha, I have to download it. Okay, so this is the survey paper. So this is a survey paper. Actually flows into diffusion. Okay, diffusion models, and the VAE is the precursor to diffusion. Means you need to know VAE first, then you can understand diffusion. Okay, so we are going to do that itself. That only. So okay, okay. So actually the some survey papers are also important papers. Because like these papers can be so complicated that we reading the paper you don't understand anything. Okay, so some person who understands it has to write more details so that you can understand. So that is why you're going through this. Okay, because the paper is complicated. You go through the papers, you don't understand. Okay, so problem was that. Okay, so we had this problem. Okay, we have to estimate this distribution px, and for that the integration is this. Okay, now this is you can write from um, the conditional distribution joint distribution thing. Okay, so now the problem is this integration is intractable, means like if z the dimension increases you cannot do the integration. Usually the z dimension is lot, 50 dimensional, 100 dimensional, 500 dimensional. Okay, can be even more. Okay, in bigger problems, the problems which Facebook or Google solves, dimension is even higher, 5000. You know how you are going to do 5000 integration, and it happens on the when you're doing the integration. Okay, so okay, so you can write this one px as integration. This can be written as px p z given x and px dz. Okay, now you're integrating over this. Then this probability distribution are also in higher dimension. Okay, so this x can be in like a million dimension. Okay, like that. And then you have to do like 500 integrations on a equation, on an expression which is million dimension. Okay, so this is not possible. Okay, that is how we move through the paper. This is the impossibility of doing this integration is the important part. Okay, now they suggest a evidence lower bound. Okay, so now you have to understand this in the expression this. Okay, so this is the evidence. Okay, so we have to make a lower bound on this. Okay, okay, so and we're going to use that lower bound for optimization. We're not going to optimize this. Okay, but we're going to do it on the lower bound. Okay, so maximizing the elbow is a proxy objective. Okay, so you don't maximize the distribution you have. Okay, but you which with which to optimize a latent variable model. So z the latent variable is important because of that reason. Okay, okay, so you can separate the two structure. Okay, now the formally the equation of the elbow is this. Okay, so the derivation is also given here. How do you get the elbow? So this is the log px. Okay, log likelihood. Okay, this is the likelihood. So log likelihood, you have to maximize the log likelihood. Okay, so am I speaking too fast, or are you able to follow? Actually there is a lot of content, that is why actually doing it. Is it okay? I mean this is for your understanding. You know, if it's not okay, if you say something, it is okay or not. mm, Nothing. Then maybe you're able to follow, huh? You're here listening some. Okay, I hope so. You know, if you're not responding, then I cannot know. Okay, so this speed is fine, huh? If I have to ask. Well, I have to take it like that, then it's fine. Okay, okay, so now you multiply and divide by q phi z given x. So previously we had previously uh, previously what we had, p z given x. Okay, now we are having q phi z given x, and phi is a different parameter. parameter of the encoder. Okay. So what you can understand is that we are introducing a proxy model. Okay. So a fake model. Okay, and approximate model, you can say something like that. So, and the best thing about this is that now the two parameters are separated. Okay, and you can control phi, but you cannot control theta. You understand? Policy is that we have some control over the parameter, so we are able to control phi so that it matches, p z given x. Okay, so try to match, we try to optimize the parameter phi such that it tends towards, it is very close to pz given x. Okay, that is the approximation we use here. Okay, so now divide multiply, so remains the same. Okay, now this is called the expectation. Okay, so what you're doing is that you're taking, means like this is called the expectation. Okay, so let me write it down. Expectation of suppose with respect to distribution q, and you have to take an expectation of p here. So what it is, integration of p multiplied q d. Suppose the variable in both of these is x. Okay, so when you are taking this expectation, so integrating with respect to z, variable in both of these is z. Okay, so you can write it like a expectation. The log is already there. Clear, right? Huh? Now you they show that you can put the log inside, and that is always lower than the original expression. Okay, so this is from Jensen's inequality. What did Jensen's inequality state? That the exact thing. Okay, log fx is so this comes from optimization actually. So the consideration is that if you have a convex function fx, okay, then this can be always written as this. Okay, okay, so the expectation is the function here. Okay, so this can be written as function of log of x. Okay, and x is here this thing. Okay, so you can write x as some another function gx. Okay, so for clearly what it is, log of f of gx is greater than equals to f of log of gx. Done, right? So this is the Jensen's inequality. Okay, now moving on, but the real derivation is here. Okay, so I think we should check out this one. So first of all, what we are doing is that you can write it in expectation form like this. Okay, expectation is clear. Now log of p x comma z by, so this is the base rule. Okay, not base rule, that one. Okay, means joint probability, px comma z is equals to px and pz, px and p z given x. Okay, joint probability can be written as a prior times conditional probability. Okay, so they have used that one. Now multiply it and divide. Okay, now you can split it into two part like this. Okay, um, very easy. Okay, nothing here. Now this is a KL divergence. So what is KL divergence? So this expression can be written as this form. Okay, this is called the KL divergence. So what is KL divergence? The definition is that uh, you're checking a probabilistic distance between the this distribution and this distribution. Okay, okay. So this is, oh, so I have written a lot of things. Okay, so you're checking the distance, probabilistic distance between the two distribution, and the one at the bottom is like with respect to this distribution. Okay, so anybody able to understand? Is it clear? Okay, please elaborate. So from this to this you can understand, right? Just division into two parts. Okay. Huh. So split into two parts. Okay, two expressions you will find in expectation. Now, what the scale divergence mean is that when whatever is in this ratio, we're checking the uh, probabilistic distance between the two. What does that mean actually? Let's see. Suppose both are normal distribution, okay, and you can say that these two have some distance between them. Okay, they're separated like this. Okay, so probabilistic distance. What does mean? There is no, like, these are not 2 points that you can measure a distance, right? So this expression helps to measure the probabilistic distance. You understand? So that is the what thing we have here, and this is in the base is the with respect to which we are doing. Okay, so keeping this q fixed, okay, you are rotating the p, means moving the p, something like that. Okay, so we are not moving it now, but when you are optimizing, okay, so then you will have to move the p. Okay, so something like that. So you can write in condensed form like this dkl. Okay, and this expectation will remain like this. Okay, now the concept is that KL divergence is always greater than 0. Okay, now if KL divergence is greater than 0, then this thing plus something positive, if you remove the something positive, then this will always be less. Okay, so this is the lower bound we have. Okay, so means this log px cannot be lower than this is the lowest value of this. Okay, okay, and what we so what does it mean? Suppose we have uh, some value here, okay, and we have this lower bound, okay, uh, that this value uh, cannot go below this. Okay, this can go below, but not below this. So this is the Lakshman Rekha, it cannot cross, something like that. Okay, now when you optimize, so I'm trying to bring this as much as up as possible. Okay, so these two are as close as possible. So it is like approximately I have learned the distribution. Okay, so optimizing, you understand, we're trying to bring it closer. Okay, when trying to optimize, I'm trying to bring px to this elbow. I'm trying to bring the elbow to the px. Okay, so that you can learn the distribution of px. Okay, so this is the concept we have here. Okay, now, so we take the elbow now. Now px is not our interest. Okay, px is done. Okay, we don't need px, we have elbow. Okay, which is called the expectation lower bound. The full form, I'm getting it wrong maybe. Let's see. Evidence lower bound. Evidence lower bound. Okay, because px is the evidence. Okay, so lower bound on the evidence. Okay, so now we go to the this part. Okay, now what we have here, that you can again apply uh, this one, right? Joint distribution is equals to product of conditional multiplied prior. Okay, so they have done that. You can see this is the one. Now you can again split into two parts. So this is the reconstruction part and this is the prior matching part. Okay, so what does reconstruction doing? What does that mean? That you are given z. So eventually after training you will have z. Okay, z you can control yourself. Increase the mu, increase the sigma, something like that. Okay, you can control the z. Okay, so it is under our control. So given z, you are able to generate the x, the image. Okay, and we will maximize that. Okay, so this we have to maximize the elbow. Okay, so we're maximizing this. Okay, so that the chance improves. Okay, and so this is in minus, so the positive part here we have to make it down. Okay, so what does that mean actually? So this pz distribution you currently don't know. Okay, after training we'll know. Okay, right? So what I am trying to do is that I am trying to uh, match the priors. Okay, so the prior generated due to by the encoder and the original. Okay, you understand? So we're trying to match that. Okay, matching the prior. So this PZ is the prior distribution. Okay, so we're trying to match the prior. Okay, so this is the loss function we have. We have to optimize it. Okay, you multiply with a minus, then you can consider as a loss. Okay, then you can minimize it. Okay, so we will use back propagation here. Okay, for back propagation we need gradient descent. Now for gradient descent the expression needs to be differentiable. Okay, so that's the next challenge we have. So for that we do this reparameterization. Okay, can be of other types as well. We consider epsilon to be a normal distribution. Okay, 0 1 normal distribution. Z is also normal distribution with different mean and variance. Okay, so this is called the reparameterization. Can be of other distributions as well, but normal is the most common one, most normal distribution. So this is the loss we have. The algorithms are shared in the paper as well. Okay, so you can go through it. It's not too tough if you understand, if you get to the loss part. Okay, okay, so we are not going through the paper. Okay, paper has one extra thing. There are two types of algorithms. Okay, so two algorithms are there. Okay, so you can see that. In short, you can see in the presentation I had made. Okay, so 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 reparameterization understood. Then you can differentiate. See, the main thing is without reparameterization you're sampling Z. Okay, so sampling process is not continuous. Okay, so it is discrete, so you cannot differentiate a discrete function. Okay, so that is why they keep Z. So Z is the variable in the expression. Okay, but epsilon is not the variable. Okay, so you can sample from epsilon. Okay, you understand? That is non-differentiable, but you are not differentiating with respect to Z, with respect to epsilon. Okay, so but Z is in the expression. Z we are differentiating. Okay, but not with we will differentiate with respect to theta and phi, and Z is a variable of theta and phi. Okay, Z is a function of theta and phi. Okay, but epsilon is not. Epsilon is not a function of theta and phi. So sampling epsilon does not disrupt the differentiability. Okay, but sampling Z directly disrupts the differentiability. But we need a differentiable expression. Understood? Let me just take some break. Okay, then I'll come back after 1-2 minutes. Okay, so we continue now. Okay, so this is the algorithm they have. Okay, so this is the lower round we have. Okay, and this we have seen the prior matching term. The reconstruction part you can write it a summation like this. Okay. Okay, so they have shown that as well in the paper. Okay, but not going through that. This is the algorithm. Okay, so you random sample from the distribution p epsilon. Okay, also have a mini batch. Okay, and then you do gradient descent, updating the loss. Okay, theta and phi, done. Okay, so these are the some of the. Okay, these are not important. Okay, so they have told the estimator is the SGBP estimator. So to estimate the parameter phi and theta, and this algorithm they have named as AEVP, autoencoding variational base. So this is the content of the paper as well. From the paper you will not get anything more. There are some derivations actually. Okay, so they have shown that you can write the one of the distribution as a in a deterministic form. Okay, which really helps. Okay, uh, and another is a approximation, something like that. Okay, so you can see it from the paper. The further derivations are there. Okay, not very hard. If you put the derivation in chat GPT, it will be able to do it. Okay, if you don't understand there. Okay, so that is the cue. So this is VAE done. Okay, now we will check some. We will check some. What will check? Forgot. So let's see some lecture notes. Yes. So what is there in the lecture notes, so you can connect better. Acha, we're starting with GAN here. Acha. So I have not done GAN here. Okay. So let's look at the GAN paper first. Okay. GAN paper is actually very different than diffusion and variation autoencoder actually, and we are doing 4 lectures in GAN. Okay, so that is a lot. So let's look at GAN first then. So the GAN paper is also here somewhere. So this is the GAN paper. I have written the gap. Okay. So a lot of introduction and no nice presentation I have made here. So you have to understand from the paper itself. Okay, no other choice. So the problem is again the same. We need to learn the distribution of the data. Okay, so this is the distribution learning problem. Okay, so we have seen VAE doing it. We learn the distribution of the data through VAE. GAN also does the same. There is another example, NC. Okay, noise contrastive estimation. So these methods that you see are generative methods. Okay, and noise contrastive estimation was a contrastive method of learning distribution. Okay, so it is an interesting paper, but it is like old paper. It's like no value of reading the paper. But if you understand, if you like the theory, then you can see that. I have read it. I like the paper. Okay, so that is there. So the problem is the same. We have to learn the distribution, but in the case of GAN we do it very differently actually. So the idea is basically that you have a generator, they call. Okay, so they generate the from a noise distribution. Means like noise distribution in, you can see in both VAE and GAN we are using some noise distribution, something like that. So it gives the capacity to the model. Okay, so that it can explore different scenarios to generate. Means like suppose you're given input of this my image, and suppose like okay, so I'm sitting here now. Now you want to generate me from like side angle. Okay, so okay, something like that. So using the noise, maybe it can generate from the side but little from the top. Some using another noise. If you repeat the experiment, then maybe somewhat from the, means like some this in this angle you're generating, another this angle. I mean side view. Okay, so it is like able to generate something like that. Okay, so noise gives the capacity to the generator. Okay, so here also you input a noise to the generator, and its outputs a distribution px. Okay, now this, yeah, px, the samples from the px you compare. So this is the fake distribution. Okay, you cannot write it px, let's say, is the original distribution, and this is the qx. Okay, so the discriminator compares which one is from the, so a sample from here and a sample from here. Okay, it compares whether the sample is from q distribution or from p distribution. Okay, so and it generates a probability. Suppose probability 0.8, so 80% chance that it is coming, whatever it has got is from this distribution, true distribution. Okay, so the our ideal condition when the training needs to stop, the our convergence criteria is this discriminator's outputs a probability of approximately 0.5. It means that it is confused that q or phi, q or p, which is different. Okay, so it is not able to differentiate. Means like we have matched the two distribution. Okay, so distribution matching. So you did not know px. Okay, now but you know qx from, because you can generate from this generator. Okay, so this is, so you've learned the distribution qx, which is copy paste of px, something like that. Okay, so you know the distribution px now. Okay, now given the distribution px, you can generate new samples and everything. Okay, following the distribution. So this is the concept of GAN. So as we have done four lectures on this GAN, so need to go to sub depth. Okay, so as you can see, this is the discriminator dx. Okay, and gx is the px is the label distribution. Wow. Okay, so the situation is something like that. So yeah, so IR. Okay, so IR, the situation is not like what you see here. Like whatever we have seen are like unsupervised or self-supervised problems. Okay, these are not supervised problem that you have a label. You don't have a label. Okay, what does the image means? Okay, we don't have the understanding. It is just an image. Okay, so the px is not the label distribution. It is the label of original images. It is the distribution of original images. Okay, suppose suppose it is a suppose everybody has switched on their camera. Okay, and I take a screenshot at the same time. Okay, so I get all the images of the people. Okay, now I want to fit a distribution through all these images. Okay, and I want to know the distribution. Okay, from which this all images can come. Okay, so that is the task we have. Okay, so px is the original distribution of the images. Okay, and there are no labels. Okay, we don't have a label data. This is not a supervised learning problem. Okay, we are up to this point. Whatever we have seen is learning the distribution. Okay, which is a unsupervised, or you can say self-supervised way of doing it. Okay, so this is the structure we have here. Okay, and so let's go deeper. So D is the discriminator here, and G is the generator. Okay, you can see. So here you can see that so you're taking expectation. What does that mean? Is that you're so when you're taking expectation, what does that mean? Is you're estimating means so you're estimating log dx. Okay, what that will be, and log 1 minus this. So you can say it is like the log of the likelihood of the uh, one for the discriminator. I mean both are for discriminator only, means like uh, so so this is the log likelihood, something like that. So taking expectation over that, okay, estimating the log likelihood, then you can maximize that, okay, something like that. So you have to understand here that there are two tasks we have. Okay, to estimate this problem, we are maximizing the discriminator, okay, and when you're written like this, it is like we are maximizing with respect to the parameters of d, okay. So what you're trying to do, you're maximizing the expression because it is a log likelihood of d, right? So we are maximizing with respect to the parameter of d, okay. So this is the maximum likelihood estimate for it. Now, but the resultant, okay, after maximizing with respect to d with the parameters of d, we are minimizing with respect to the parameter of g, okay. So what it means is that first you are maximizing the log likelihood of with respect to d. So with what it means is that you are able to train the d, okay, and for that next we are minimizing the expression with respect to g, okay. So 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 maximizing likelihood with respect to d means that we have trained the decoder or discriminator model, okay. uh, and for training the generator model, we are minimizing it, okay. So what we are trying to minimize here, you can see uh, mm, so let's understand the expressions first, okay. So what we are doing is that when it is the data is sampled from the original distribution, the the this should give one, right? Discriminator uh, should give one, okay. And if it is sampled from the fake distribution, okay, then the discriminator should give 0, okay. So 1 minus 0, still 1, like that, okay. And now you can see that we are getting the gz only in this part when we are sampling from the fake distribution, okay. Now the thing is that okay, now the thing is that I don't want this discriminator to produce 0 in this case, right? If you can understand, I want it to be more, okay. It is like close to 1, okay. So that it get confused, okay. Understand? In the perfect scenario, when the discriminator is super strong and the generator is not able to understand anything or produce anything significant, then it will produce 0, means like it is clearly from the fake distribution, okay. But I don't want this. To optimize it, I need to increase the output of the output of this expression, okay. Okay. So so what it means is that in the ideal scenario of this maximizing of d, okay, so it is so strong that it is able to produce 0 here, but we don't want that, okay. So for that we minimize with respect to g with the parameter of the g, so that the d does not get too strong that to produce 0 perfect zeros, it is like somewhat higher, okay. So that is the concept we have here. Understood? So it is a complicated problem actually. These are like game theoretic setup, okay. So I explained it in an intuitive way, but this is a complicated problem, okay. And the solution is something like you cannot optimize both of the parameters, okay, at the same time. So they settle in a, you can say, samjhauta, okay, a understanding, okay. That understanding, that some level where discriminator and generator both are working well, okay, but not too well, okay. So this is the samjhauta or like agreement, okay, you come to. You cannot optimize both of them together, okay. So in optimizing both of them, okay, let me get into it, okay. So this agreement is called the Nash equilibrium, okay. So in game theoretic understanding, we have settled into a Nash equilibriums means you cannot optimize completely both of the parameters. Okay, so just if you can understand, if we optimize the discriminator completely, then it will be able to distinguish between the two images perfectly. Okay, so you don't want that. Okay, and another is that if you train the generator so strong, you're making it strong, but the feedback loop comes from the decoder itself. That yeah, if if the decoder says it is fake, then only the generator tries harder to improve itself. Okay, so if you have made the decoder very weak and generator very strong, the generator does not get strong. It should be like that. Okay, so that is the a minute balance between the two is required. Okay, so this is the Nash equilibrium thing. uh, Understood, right? And what more thing we have here? uh, there are some derivations here which are interesting but not so important. So you can see this is the distribution matching. They're coming closer together, okay, until they match. Okay, okay. So we can get through the questions here actually. So given an input x and output y, which of the following is the quantity of interest in discriminative modeling? So this is a discriminative task. Okay, the discriminator you had uh, in the GAN. Okay, but the task we have seen is the generative modeling. We need to generate. Okay, so this is like our discriminator is like doing classification, regression. Okay, these are the discriminative tasks. Okay, so PX is not a GAN in not interest, right? It is the interest in generative modeling. Okay, and the output is y. So output is the label that you have asked. Okay, so output is the label. So what we try to do is we try to output the label in a discriminative task, right? Is this a dog or is this a cat? Okay, so what we are doing is this one. Okay, so this is our answer. Clear? Understood. Next, what you have, which of the following is the correct way of training generator and discriminator in GAN? First, train the generator completely, and then train the discriminator. So the theoretical thing is that you train both of these together, okay? But it actually does not work in practice. Okay, discriminator usually gets strong very quickly, and it does not allow the generator to get stronger. So what you have to do is you have to train the generator first, and then after some time start the training of the discriminator. Okay, that part is not there. Okay, means like theoretical way is doing them alternately. Okay. So but in practice sometimes you see that generator gets discriminator gets strong very quickly, and then generator cannot improve. Okay, so I told that I thought that it was that part. Okay, but theoretically it should work together well, and in the paper you see that they are some once maximize with respect to d, then minimize with respect to g, maximize, minimize like that. So third inception, Frechet inception distance, I don't remember. Okay, I have not seen the lectures. Okay, I think you can do this one. Okay, whatever that is. Okay, which of the following is true? The encoder and decoder of a VA must contain only convolutional layers. Feed forward net to connections are not allowed. Okay, so that is what they say. So that's not correct actually. Prior distribution of a on latent space of VAE should always be Gaussian. This is also not correct. Can be any distribution. Okay. Output of the decoder generated in VAE does not need to be an image. This one is correct. Okay. So in many thing actually. So actually I was just before this lecture I was looking at graph VAE. So you are trying to generate a graph. Okay, molecular graph out of the VAE. Okay. So there can be other than images. Okay. So this one is also wrong. Which of the following is not a desirable property of deep generative model? Learning good generalizable latent features. Learning to generate new. So answer is 5C of course, because we are not trying to generate the same samples that we have encountered in the training. Okay, there is no meaning of that. Okay, trying to generate new sample. If we already have something, why would you need to generate it? Okay, so answer is that. Any doubt here? Encoder decoder architecture in VAE. Okay, it can be a CNN and vision transformer. You can have some feed forward. Uh, you can have some feed forward connections as well. Okay, so it doesn't matter actually. Any neural network works actually. Even using simple neural network, you will get not so good result, but theoretically it is also okay. VIT gives the best performance. Any doubt? In real world, VA needs to generate images. That is correct, yes. But as I said, this see VA is not the best image generator. Okay, VA is usually mostly needed for extracting the latent representation. Okay, the latent that Z you have seen, extract that actually. VA image is actually really bad actually. So you can check in the paper. Maybe I can show as well. The images are really bad. It is able to generate something, but they're not what you see from ChatGPT. Uh, so VAE, this is the one. Images they had shown, I think. So the faces are really bad. They're doing simple tasks like numbers here. Okay, generating numbers. High quality images you cannot generate with VAE. Okay, so that is the thing. Okay. So VAE is just the first step towards generation. Then we get to diffusion models, which are good quality image generator. Okay, there are also other improvements. Okay, for diffusion models, but the modern modern methods which you use in Chat GPT uses some form of diffusion only. Okay, but they're also improved. Okay? They're better than a simple diffusion model. Okay, so that part is there. Okay. uh, yes, they have used MNIST to train. Okay, okay. Yes, they have used MNIST. So they cannot use generate my picture here, as you can see, as I can see. So not so good actually. VA was the first one. Okay, but currently VA is very important still. Okay, but not for generation, for for producing the latent representation, which actually I am also using in my research. Okay, making new VAs, new type of VAs. Okay, for generating representation. Okay, the latent representation Z you have seen. That is the importance of VA actually. That generation quality is bad in VA. You get good in diffusion. GAN is also a good generator. You can see the pictures in the GAN as well. I'll show. Pictures are not good. Okay. GAN still tries to do on real images. VA does not even try. So you can see the pictures. Okay. Very bad actually. MNIST it has done well because it is too simple. Other than any real world images are too bad. This is in GAN. Okay. Diffusion is a better one. Okay. Big GAN is decent. But like these days the generation quality is something else. No? For generation exclusively all models use diffusion. Better form of diffusion. Okay. Not any other model. Diffusion is the extension of VAE. So you can read it from the survey paper. I'll upload it tonight. Okay. But that's it. Okay. So we're going to finish up early today. Okay. Any doubt? They keep same value of pixel to generate more images. Same value of pixel to generate more images. What does that mean? GAN. Same value of pixel. What do you mean by same value? It has to be stochastic. You cannot deterministically generate. Okay. These methods are all stochastic method. Okay. Any deterministic component, then it will never work. Actually, cannot fix a pixel of value. Cannot fix a pixel value. Okay. That pixel value minus 200. If you keep pixel value minus 200, it will generate minus 200. How can it work? You can unmute and say what you're trying to say. Maybe you're saying something else, I don't know. I have not gone into the experimental details of the paper, the theoretical I have done it. Okay. GAN are also important many other VA in GAN are important many other areas. Okay, but in generation they are like the quality is so bad then that we don't use it anymore. They fail at good quality generation. Okay, diffusion is the way to go. Okay. Understood? There are also better models, okay, but they are of the diffusion style only. They are called full flow models. Diffusion also a flow based model, okay. Please diffusion, upload diffusion other papers in Drive, okay. I will do it at midnight today, okay. Right at 12, okay. After this I will be busy, okay. But at midnight I will do it. Because if the PhD student is busy, then only the lectures are good, right? Knowledge has to be there. Okay. Thank you very much. Any doubt? Or you have doubt? Achha, yes can mean many things. Okay. Any doubt? You can ask them. No doubt. Okay. So you're telling that PhD busy thing. Okay. Thank you everyone. Any doubt? Yeah, still again. Can you also share collab code files for practice? Okay, if possible. Okay, the thing is that I have not actually coded on collab these assignments actually. I think other TAs will do it actually. Uh, that is it. Okay. You can take it from other TAs actually. I've actually not done the collab codes. Okay. Okay. Can you share your email ID? Sure. This is also the IIT Delhi ID. Okay, we are done then. Okay, I'm finishing it here.